Hello and welcome to Algebra 2 Lesson 20. In this video, we're going to learn about linear inequalities in two variables. So once we've mastered the art of graphing a linear equation in two variables, you're going to find that it's not much more difficult to master the art of graphing a linear inequality in two variables. So we start out with a basic form. This is something you'll see in your textbook. So a linear inequality in two variables is of the form ax plus by is less than c, where we would say a, b, and c are real numbers, and then a and b are not both 0. Now also, this less than symbol here could be a greater than, it could be a less than or equal to, or it could be a greater than or equal to. Now when we talk about graphing a linear inequality in two variables, when we look at our coordinate plane, it's going to have three distinct regions. So the first region I'm going to talk about is the solution region. So this is where we have any ordered pair. So we have x comma y that satisfies the inequality. The next part I would talk about is the non-solution region. So this is any xy or any ordered pair that does not satisfy the inequality. So you have two separate regions. Now these regions are separated by something known as a boundary line. So the boundary line is a line that separates the solution region from the non-solution region. Now, the key thing to understand here is that this boundary line can be part of the solution or it can be not part of the solution. It's based on what type of inequality you get. If you get a strict inequality, meaning you get a greater than or a less than, right? This is strict, then the boundary line is not part of the solution. Okay. If you get a non-strict inequality, meaning you have greater than or equal to or less than or equal to, this is non-strict, then in this particular case, your boundary line is part of your solution. All right, so let's talk a little bit about how we actually go about doing this. It's quite similar to, again, graphing a linear equation in two variables with just a little bit of a twist to it. Now, there's two kind of ways to do this. One way is a little bit slower. It involves something known as a test point. And then the other way involves just solving for y. So I'm going to go through both procedures for you, and then you can choose which one is better for you. So graphing a linear inequality in two variables. The first thing we want to do is replace the inequality symbol with an equality symbol, then graph the resulting line. This is how we get the boundary line, okay? When we do this, if the inequality symbol, again, is strict, then we want a dashed line because the boundary line in that case is not part of the solution. If the inequality is non-strict, we want a solid line because in that case, the boundary line is part of the solution. Now, the next thing we want to do is we want to choose a test point. So this is any ordered pair that is not on the line. So you just plug it back in to the original inequality and you see if it works. So if it does work, you're in the solution region. So you shade that region where the test point is. If it doesn't work, then you're in the non-solution region and you just shade the other side. All right, so let's start out with the first example. We have 2x plus y is less than 3. So the first thing I want to call your attention to is that this is a strict inequality. So that tells me that my boundary line is going to be not part of the solution. And so I want a dashed line. Usually what I do is I'll take and draw either, gaps in my line or I'll draw a solid line and then kind of erase it, depending on what method I'm drawing with. If I'm on a computer, then I'm going to break it up. If I'm drawing it with a pencil, then I'll just kind of gap it. So we have a strict inequality. The boundary line is dashed or broken. Now, the other thing I would call your attention to is that it's not solved for y right now. And I'm going to get to that in a minute. So all I'm going to do is I'm going to replace this with equals. So I'm going to pretend like I have 2x plus y is equal to 3. I'm just going to graph this. This is going to be my boundary line. This is the boundary. So this will separate the solution region from the non-solution region. Okay, so we know how to graph this. Let's get some points going. So if x is 0, y is 3. If, let's say, I don't want to use the x-intercept because that's going to give me a non-integer. But let's go ahead and say if x was negative 2, I would have 2 times negative 2 plus y equals 3. So this would be negative 4 plus y equals 3. Add 4 to each side, and I get y is equal to 7. So if x is negative 2, y is 7. And let me get one more point going here. Let's say x is positive 2. So I'd have 2 times 2, that's 4, plus y equals 3. Subtract 4 away from each side of the equation. I'd have y is equal to negative 1. So I have 3 points there, 3 ordered pairs. And I'm just going to plot them on the coordinate plane. So 0, 3, negative 2, 7, and 2, negative 1. So 0, 3, that's going to be right here. Negative 2, 7. So I go 2 units to the left, 7 units up. It's right here. And then 2, negative 1. So that's going to be right here. So again, this line that I'm going to draw right now should be broken or dashed. So because I'm drawing this on a computer, I'm just going to draw a straight line, then use an eraser to break it up. Okay, and then let me get my eraser. Okay, that should be good enough. So you just want to make it obvious that you have a broken up or dashed line. Again, a broken line means that the line is not part of the solution. If you have a solid line, it is part of the solution. And I'll give you an example of this. If I take 0, 3, let's go back up, and I plug that in, because 0, 3 is on the line, and this is a strict inequality, it should not work. So let's see if it does. So we have 2 times 0 plus 3 is less than 3. 2 times 0 is 0, so this would cancel. You'd be left with 3 is less than 3. Well, that is not true. 3 is not less than 3. 3 is equal to 3. But if this was a non-strict inequality, let's say, for example, I had less than or equal to over here. Well, then when it gets to this, 3 is less than or equal to 3. Well, that would work. So you can see that your boundary line is part of the solution if you have a non-strict inequality, but not part of the solution if you don't. Okay, so in this case, we've got a strict inequality, so it's not part of the solution. Now, the next thing we want to do is we want to choose a test point. So let me go back to the coordinate plane. You want to look for something that is not on the line. The most common test point you'll use is 0, 0, because it's nice and easy to work with. So you're going to say, is 0, 0 a solution for that inequality? If it is, I'm going to shade everything in that region. If it's not, I'm going to shade everything in the other region. So I go back up here, and I say my test point is 0, 0. So I just plug in. So I say 2 times 0 plus 0 is less than 3. 2 times 0 is 0, so that's gone. Plus 0 is 0. So you get 0 is less than 3. That's true. So if this is true, that means that 0, 0 lies in the solution region. So that means that everything over here satisfies the inequality, and everything on the other side of the boundary line does not. And you could choose a test point over here and see if it doesn't work. So something like, let's say 4, 1. So this is in the non-solution region. Non-solution region. And let's say we look at 4, 1. So I would have 2 times 4 plus 1 is less than 3. 2 times 4 is 8. 8 plus 1 is 9. 9 is not less than 3. So this is false. And we expect it to be false because I took a point that was in the non-solution region, right? It should not work, and it didn't. So that's good. But when we look at this, again, this is the non-solution region. Over here is the solution region. So typically we will shade this, and depending on what you're working with, if you're in class, right, you don't have a computer, you would just kind of shade in the direction of the solution region. So I'll show you this. I'll just take a black marker and just shade here. Put arrows at the end to say, hey, this continues forever in this direction. Anything on this side of the line would satisfy that linear inequality in two variables. Okay. So again, you can see three distinct parts. Non-solution region, boundary line, which in this case is not part of the solution, and then your solution region. Okay, three parts. Now, let me talk a little bit about how to do this in what I would say an easier fashion. So let's erase everything here. Now, some textbooks will cover this, others will not. And again, it's a matter of personal preference. I don't like using a test point. I just think it's very slow. What I do personally, and what a lot of teachers will have you do, is just start out by solving the inequality for y. Okay, so remember, if you have an equation solved for y, it looks like this. Y equals m the slope times x plus b. In this particular case, it's an inequality, but we're going to just put it in this format. So I'm going to subtract 2x away from each side. I'll have y is less than negative 2x plus 3. Now I'm going to replace this with an equality symbol. So I'm going to have y is equal to negative 2x plus 3. And I'm still going to draw my boundary line. This is still the boundary. And it's still going to be a dashed line because this is strict. But how would I graph y equals negative 2x plus 3? So y equals negative 2x plus 3. Well, I have a y-intercept that occurs at 0, 3. So that's right here. So I would start out by using that point. And my slope is negative 2. So my rise over my run is negative 2 over 1. So I would fall 2, 1, 2 to the right 1. Fall 2, 1, 2 to the right 1. So I would draw my boundary line based on that. So I get the same exact line. Now, here's where the fun part comes in. If I've solved this for y, I don't need a test point. All I do is look at the symbol that I'm given. If I have a less than, I shade below the line. So that's a less than or a less than or equal to. Let me kind of slide that down. Less than or less than or equal to, shade below the line. If I have a greater than or a greater than or equal to, I'm going to shade above the line. It's very, very simple. So if I look at this, this is a less than. So I just come back to the graph. Once I have the line, I just shade below it. And that's exactly what I see there. So look how much faster that would have been versus using kind of the slow method. And then on top of that, finding a test point, going back to plug it in, seeing if it works, then shading. So I think the test point method is quite slow actually. And solving the linear inequality in two variables for y is definitely the way you want to go. So let's take a look at another one now. I'm going to use both methods for one last time. And then from here on out, I'm just going to solve this guy for y. I'm going to kind of blow through these. I'm going to do it by solving for y first though. So I'm going to subtract 4x away from each side. That's going to give me y is greater than or equal to negative 4x minus 1. Now to get my boundary line, I just replace this with equals. So I'll have y is equal to negative 4x minus 1. Now I want you to notice something. This is a non-strict inequality. So in this particular case, my boundary line is solid, right? Because points on that line will satisfy the inequality. So if I graph y equals negative 4x minus 1, so y equals negative 4x minus 1, my y-intercept occurs at 0, negative 1, so that's right here. My slope is negative 4. So again, rise over run, it's negative 4 over 1. So I fall 4, 1, 2, 3, 4, I go to the right 1. I fall 4, 1, 2, 3, 4, I go to the right 1. Or I can think about this as 4 over negative 1. So I could start here and I could go up 4, 1, 2, 3, 4. I can go to the left 1. So now when I sketch this graph, remember this is a solid line now. This boundary line is part of the solution. All right, now the next thing I'd look at is the fact that this is a greater than or equal to. So for a greater than or equal to, I shade above the line. So I come back here. If I want to shade above the line, I would shade this direction. Just make it completely clear to your teacher or whoever's grading your test that this is the solution region, and then this over here is the non-solution region. So again, you've got three different parts here. You've got a non-solution region where ordered pairs do not satisfy the inequality. You've got a boundary line, which in this case will satisfy the inequality. And then you've got a solution region. Okay, so three parts here. Now, you saw how quickly we did that. Let's erase all of this. Let's do this the slow way using a test point. So I'm just going to start out again by replacing this with equals. So I would have 4x plus y is equal to -1. And let's get some ordered pairs going. So let's say x is 0. We know y equals -1. Let's say that x is -2. We'd have 4 times -2 plus y equals -1. 4 times -2 is -8. So I'd have -8 plus y equals -1. Add 8 to both sides of the equation. That'll cancel. You'll get y is equal to 7. Let's try something simple for x. Let's try 1. So if x is 1, 4 times 1 is 4, plus y equals -1. Subtract 4 away from each side of the equation. You get y is equal to -5. All right, so I have three ordered pairs there. So I've got 0, -1. I've got -2, 7. And I've got 1, -5. All right, so 0, -1 is right here. -2, 7. If I go 2 units to the left and 7 units up, that's right there. And then 1, -5, if I go 1 unit to the right and 5 units down, that's right there. So my points are there. I would draw my solid boundary line. And then I would have to choose a test point. In this particular case, I can still use 0, 0 because it's not on the line. So I would go back up here and I would say 4 times, again, my test point is 0, 0. So 4 times 0 plus 0 is greater than or equal to -1. So you'd end up with what? 0 is greater than or equal to -1, and 0 is greater than -1, so that is true. So that would tell me that I need to shade above the line. And again, that's what I already found. So using a test point works. It's just a little bit slower in my opinion. Using this method where we solve the inequality for y allows you to graph the boundary line faster, right? Because you can graph based on the slope and the y-intercept. And it allows you to shade the line faster because you shade based on whether it's a greater than or equal to, or less than or equal to. Okay, so in all aspects, in my opinion, it's just simply faster. All right, so let's look at another one. And again, I'm not going to use a test point anymore. So let's solve this guy for y. So we have 5x minus 3y is greater than or equal to 15. If I solve this for y, I'm just going to subtract 5x away from each side. That's canceled. I'll have -3y is greater than or equal to -5x plus 15. Now, very important that you remember this. If I divide both sides by -3, what do I have to do? I've got to flip the direction of the inequality symbol. If this is a greater than or equal to, I've got to make sure to make this a less than or equal to. Otherwise, I'm going to get the wrong answer. Right? I'm not going to shade in the right direction. So this cancels with this. I've got y is less than or equal to. -5 over -3, we just write 5/3. Then times x. And this is minus 15 over -3. I've accounted for the negative. 15 divided by 3 is 5. So -5. So I've got y is less than or equal to 5/3 x minus 5. So let's erase this. Pull this up here. And again, I still want to graph my boundary line. So I'm just going to replace this with equals. So my boundary line, I would have y equals 5/3 x minus 5. Now again, because this is a less than or equal to, it's a non-strict inequality. So that tells me that points on the boundary line will satisfy the inequality. And so I want a solid line. All right, so to graph y equals 5/3 x minus 5, I know the y-intercept here is at 0, -5. That's right here. And my slope is 5/3. So my rise over my run is 5/3. So up 1, 2, 3, 4, 5. to the right 1, 2, 3. Then again, up 1, 2, 3, 4, 5, to the right 1, 2, 3. And let me erase a little part of that. It's a little long for us. So I'll put arrows at each end. So this is my boundary line. Again, it's a solid line because we have a non-strict inequality. Now, if I go back to my page, I see that when I solved it for y, I have a less than or equal to. So that means I'm going to shade below the line. Again, it's got to be solved for y. You don't want to look at this original guy. Make sure it's solved for y first. Y is less than or equal to, so that means I shade below the line. So if I want to shade below the line, I would shade this way. So anything shaded that's in the solution region, the boundary line is part of the solution here. And then anything over here above that line is in the non-solution region. So these points will not work. And you can always grab a test point to check. You can take 0, 0. Notice that's in the non-solution region. So if we plug it in, it should not work. So if I go back up here, I can take and plug it into this one or the original, doesn't matter. So 5 times 0 minus 3 times 0 should be greater than or equal to 15. Again, this shouldn't work. So we expect this to be false. This will cancel, this will cancel. You'll get 0 is greater than or equal to 15, which is false. 0 is not greater than 15, and 0 is also not equal to 15. But again, that's what we expect because 0, 0 is in the non-solution region. All right, so let's talk about some special case scenarios now. Let's say you came across y is greater than 1. And you're like, what do I do there? Y is greater than 1. Well, I want you to remember a few things here. For one, if you had y equals 1, this is a horizontal line. This is a horizontal line. So to graph this, I would go to my coordinate plane. And again, I'm thinking about y equals 1. So find 1 on the y-axis. It's right here. I would just draw a horizontal line. So this would be y equals 1. When we look at this, we see that this is a non-strict inequality. This is non-strict. So we know that points on the line will not satisfy that inequality. So what we do is we make this a dashed line. So y is greater than 1. We would have a dashed line. So let me take my eraser now, and we will break this guy up. And again, this identifies that points in this line are not part of the solution. Now, if y is greater than 1, what does that mean in terms of a solution? Well, that means anywhere on the y-axis that's larger than 1 is a solution. So that means I would shade above the line, because if y is 4, 4 is greater than 1. If y is 8, 8 is greater than 1. Anything below the line doesn't work. If y is negative 1, well, that's not greater than 1, so that wouldn't work. So this down here would be the non-solution region. And anything above the line would be the solution region. So I would shade this way. And again, how do you check something like that? Well, formally, again, if you think about something like 0x plus y is greater than 1, well, if I choose a point where y is greater than 1, it's going to work out. So if I choose a y of like, let's say 5, for example, x can be whatever. X could be negative 30. So let's say I have the point negative 30, comma 5. Plug in a negative 30 there. Plug in a 5 here. Negative 30 times 0 is 0, so that's canceled. You'll get 5 is greater than 1, which is true. So it doesn't matter what the value of x is. It's irrelevant. As long as the y value is larger than 1, we have a true statement, which is why on our coordinate plane, we just shaded everything above the line. Again, you're just looking at y value. So you're only looking at the y-axis in this case, and anything on the y-axis that's larger than 1 going up is going to work as a solution. All right, so as the other special case scenario, let's say you saw something like x is less than or equal to negative 3. So you can almost guess what this is, right? If I graph x is equal to negative 3, what does that look like? So x is equal to negative 3. I find negative 3 on the x-axis, and I draw a vertical line. Now, in this particular case, we have x is less than or equal to negative 3. So the boundary line is a solid line, so I don't need to break this up because points on that line will satisfy the inequality. If I have x that is actually negative 3 is less than or equal to negative 3, that's true because negative 3 is equal to negative 3. Then also any x value that is less than negative 3 will work. So how do we get less when we're talking about the x-axis? Well, we go to the left. So thinking about x values that are less than negative 3, I would shade to the left. Just have to think about this in terms of x values only, because it doesn't matter what the y value is. Y value can be whatever. If I wrote this as x plus 0y is less than or equal to negative 3, you could choose a y value as high or low as you want. Let's say you choose 10, for example. So if I choose an x value that's, let's say, negative 6 and a y value of 10, this is going to work because my x value is less than negative 3. Plug in a negative 6 there. This would cancel whatever it is. 0 times anything is 0. So negative 6 would be less than negative 3, so that would work out. If you choose any x value that is greater than negative 3, it won't work out. In other words, if I plug in a 1 here, and let's say I use 10 here, well, 1 comma 10 won't work because, again, this cancels. 1 is not less than negative 3, and it's certainly not equal to negative 3, so that won't work. So again, when you're shading here, just think about that. Any x value that's less than negative 3 or equal to negative 3 would work. So you've got a solid line at negative 3, and you've got values to the left of negative 3 all shaded. Okay, so we're just going to wrap up the lesson now by talking about compound inequalities again. So we looked at these when we talked about linear inequalities in one variable. You will see them when you talk about linear inequalities in two variables, but again, this stuff is not more complicated. It's a little bit more tedious because we've thrown another variable in there, but graphing this should not be mentally challenging for you. You think about the two different words that you're going to come across. You have and then you also have or. When you see a compound inequality with and, remember you're looking for the intersection of the two solution sets. So in order to say it's a solution for the compound inequality, it has to be a solution for both. So graphically, I'm looking for the section of the coordinate plane that's the overlap, right? It satisfies both inequalities. If I'm thinking about or, right, the keyword or, well, in that case, it could be a solution to either, right? So it could be a solution to one and not the other, or it could be a solution for both. It doesn't matter because it could work for either. All right, so let's just look at this one problem here. When we go into our practice set, when we go into our test problems, we'll see a scenario with or. Here, we're just going to see a scenario with and. But again, if we looked at or, we'd know the difference is it could be a solution for either. So we look at x plus y is less than 3, and negative 3x plus y is greater than or equal to negative 1. So again, I'm just going to start out by solving each for y. I'm going to graph each, and then I'm going to look for the overlap. So let's start out by subtracting x away from each side over here. So that's going to give us y is less than negative x plus 3. And then for this guy over here, I'm going to add 3x to each side. So that's going to give us y is greater than or equal to 3x minus 1. So let's go ahead and take these two down to the coordinate plane. We'll just copy them. And we're going to graph each one separately. And then we're going to look for the overlap of the two graphs. So for the first one, y is less than negative x plus 3. Again, to draw the boundary line, I would replace this with equals. So if I had y equals negative x plus 3, how would I graph that? Well, the y-intercept is at 0, 3. So that's going to be right here. And then the slope is negative 1, right? So that's rise over run of what? Negative 1 over 1 or 1 over negative 1, whichever you want to do. So I can fall 1, go to the right one, or I could rise 1, go to the left one, whatever you want to do. Again, if I have enough points to draw a straight line, then I'm good to go. In this case, you have a negative 1, so I could say negative 6 over 6 if I wanted to. So I could follow 6, 1, 2, 3, 4, 5, 6. Go to the right, 1, 2, 3, 4, 5, 6. That's the point on that line, because negative 6 over 6 is negative 1. I could also rise 6 and go to the left 6 if I wanted to. But the reason I did that was to get a point down here so I could kind of put my ruler in a row and get a nice clean line. Okay? You only need 2 points to make a line, but it's just so much easier if you have more points involved so you can make a nice clean line. All right, so now that I'm going to draw this, remember, this is a strict inequality, so I want a broken or dashed line. Okay, so I'll draw my line to start, put some arrows there, and what I want to do is just take my eraser now, and I'm just going to break it up to let people know if they're looking at this, this line is not part of the solution. Okay. Anytime you see a dashed or broken line, you know it's not part of the solution. All right, now we have a less than. So if we have a less than, we're going to shade below the line. So I want to shade below the line like that. Let's look at y is greater than or equal to 3x minus 1. In this case, I'm just going to erase this. And I'm just going to change this to a stroke eraser. I can erase quickly. In this case, I have y is equal to 3x minus 1 for my boundary. So I'd go to 0, negative 1, which is here. And my slope is 3. So rise is 3 over run, which is 1. So up 1, 2, 3, go to the right 1. Up 1, 2, 3, go to the right 1. Or I could fall 1, 2, 3, go to the left 1, right? Because 3 over 1 is equal to negative 3 over negative 1. Again, think about those tricks. So I'm going to draw this line in green, and this line right here is going to be a solid line because this is a non-strict inequality. Okay, so this is a greater than or equal to, so I want to shade above the line. So I'm going to do that in an orange. If I'm looking for the overlap, the section on the coordinate plane that satisfies both, the thing that I want to do, the thing that makes it easier for me, I'll take a black marker and I'll start lining out stuff that does not work. So in the first case, y is less than negative x plus 3. We know we have this blue dashed line. Any point that was below that line worked as a solution. So any point above the line doesn't work as a solution for this inequality, and therefore doesn't work as a solution for the compound inequality because it has to work for both. So I can just take a little black marker or whatever, a pencil, and just mark this section out and say, hey, this is not going to be part of the solution for the compound inequality. Then I'd look at the next part. Y is a greater than or equal to 3x minus 1. Okay, well that was this green line here. So anything above the line worked, anything below the line didn't. So this is where it's below the line, and that does not work. Now, what's interesting here is that the green line in this case is actually part of the solution. With the blue line, it's not, right? It's the difference between a strict inequality and a non-strict inequality. But when I look at the overlap, I'm just going to highlight this with a normal highlighter now. The green line here, starting at this intersection point, is included. So I would highlight all the way down here. And at some point I have to stop, but this is an infinite area. Then all the way over here. Then all the way up here. And then all the way here. And then this blue line here is not included. So I'm just going to highlight that. So the green line that's highlighted here, that's included. The blue line, not included. And then I'm just going to shade everything here in this area. This is the section of overlap, or the part of the coordinate plane that satisfies both inequalities. And so this is the solution for the compound inequality with and. Now, if you had had a compound inequality with or, again, you would be highlighting the sections that satisfied either, right? It wouldn't matter if it satisfied both. It would be what satisfied either one. But for our problem here, we had and. So this is a good representation. Of course, you can always make it better if you wanted to. If you wanted to get a little bit better, we could erase this arrow here. And And we could kind of extend this line a little more. And let me get my highlighter again. I'll just kind of highlight a little bit more here. Just get a better representation, a better visual aid here. But you're basically saying to your teacher, hey, anything that's above the green line, right, starting right here, going to that intersection point, and including that green line, that is also below the blue line, not including the blue line, is the part of the coordinate plane that satisfies both. And so that's your solution for the compound inequality, in this case with and.